We have long viewed Mars as a possible second home. However, as we delve deeper into the exploration of our solar system, new candidates emerge, some potentially even better suited for colonization. Life on early Earth was vastly different from what we see today. The atmosphere was distinct, dominated by completely alien species, and the landscapes of that era would be unrecognizable to us now. Therefore, as we search for potentially habitable celestial bodies, we should broaden our criteria and consider the conditions that might support the existence of alien life forms. There is one world in our solar system that fits these criteria. How does Titan mirror early Earth? What are these enigmatic deserts on Saturn's largest moon? And what triggers the eruptions of its lakes? Titan, with a diameter of 3,200 miles (5,150 kilometers, is the largest among Saturn's 146 moons, even surpassing the size of Mercury. However, this moon is anything but ordinary. In fact, Titan bears such a striking resemblance to Earth that it almost seems surreal. Not only does Titan boast lakes, seas, and rivers, but it also harbors a subsurface water ocean located 50 miles (80 kilometers) beneath its icy crust. Above its surface, Titan's skies are adorned with clouds, while its terrain is rich in organic compounds. Rainfall occurs on Titan, replenishing lakes and seas with liquid bodies that later evaporate, creating a hydrological cycle akin to Earth's. The atmosphere surrounding Titan, composed of nitrogen and methane, is dense enough to allow for casual strolls on the moon's surface without the need for a pressure suit. However, Titan's extreme cold of 290F179c and its lack of an oxygen-nitrogen atmosphere like Earth's present significant challenges. Interestingly, with wings attached to your suit, you could soar through the skies of Titan, as the moon's gravity is only 14% of Earth's. This would offer a unique experience of observing raindrops fall in slow motion, about 6 times slower than on Earth. Remarkably, rain on Titan consists of liquid methane, with droplets approximately 50% larger than those we encounter on our home planet. Titan is situated approximately 750 million miles (1.2 billion kilometers) away from Earth, orbiting Saturn in a 16-day cycle, while being tidally locked to the 6th planet. Despite one side of the moon always facing Saturn, Titan exhibits intricate weather patterns. As Saturn's largest moon, Titan receives 100 times less solar energy than Earth and boasts a thick atmosphere that extends 10 times higher into space, limiting the amount of light that permeates through to its surface. During the initial half of Titan's day, equivalent to 16 Earth days, its surface is ensconced in a gentle orange haze, resembling the challenge of seeing through thick smoke from a fire. The daytime skies on Titan could be dimmer by 100 to 1,000 times compared to an afternoon on Earth. The latter part of the day plunges the moon's surface into complete darkness, further obscured by the persistent haze that obstructs views of Saturn. Interestingly, the brightest phase of Titan's day isn't daytime, but rather twilight, which computer simulations suggest can be up to 200 times brighter than during the day. This phenomenon occurs due to the scattering of light by haze particles in the atmosphere. Being tidally locked, Titan maintains a continuous daylit side and night side, leading to the existence of a permanent twilight zone known as the terminator, marking the border between the illuminated and dark sides of the moon. Titan, akin to Earth, witnesses eclipses that can extend up to 6 hours, resulting in a scenario where a second night occurs in the midst of the day. This phenomenon would be noticeable only from Titan's side facing Saturn. Otherwise, a solar eclipse would transpire during the moon's nighttime. The occurrence of eclipses aids scientists in gauging the amount of sunlight reaching Titan's atmosphere and surface, crucial for understanding the environmental conditions that potential life on Titan would need to endure. Recently, The James Webb Space Telescope successfully identified clouds forming in Titan's lower atmosphere during late summertime, correlating with increased heat absorption on its surface. This discovery validates the presence of seasonal weather variations on the Moon, aligning with scientific predictions. Notably, Titan's axial tilt in relation to the Sun closely mirrors that of Saturn, resulting in both celestial bodies experiencing seasons of roughly equivalent duration, cycling approximately every 7 Earth years. Although at a slow rate, seasonal shifts bring changes in weather on Titan. Similar to the Earth, when Titan's axis is tilted neither away from nor toward the Sun, a fascinating event occurs. Imagine an axis cutting through the North and South poles, splitting the celestial body in half. During such times, which happen twice a year on Earth, night and day are approximately the same length globally. This phenomenon, known as the equinox, also happens on Titan, though less frequently, about every 15 years. During these equinoxes, enormous methane clouds form in Titan's equatorial regions, resulting in severe wind storms. In Titan's summertime, the winds grow even stronger. Observations from the Cassini mission revealed waves on Titan's lakes that differed significantly from those on Earth. Titan's low gravity allows these waves to rise much higher, about 7 times taller than those in Earth's oceans, though they move more slowly, up to 3 times slower. Additionally, Titan's winds can stir up powerful dust storms, a phenomenon also observed on Mars, wherein big dust clouds form head of storms. These storms help spread organic dust around Titan's surface. Despite downpours being a rare occurrence on Titan, when they do happen, they leave a substantial mark on the landscape. Titan's heavy rains significantly impact its surface, creating structures known as alluvial fans. These features resemble triangular piles of dirt and rocks, formed when flowing water or ice deposits the materials it carries. Scientists have also detected vast dune fields on Titan that cover up to 13% of the Moon's surface. These dunes are colossal compared to those on Earth, stretching hundreds of miles long, 1.2 miles 2 kilometers wide, and towering 330 feet 100 meters high. Titan boasts more sand than any other celestial body we know, albeit this sand isn't composed of silicates like on Earth. Instead, it consists of solid hydrocarbons that descend like rain from Titan's dense atmosphere. On Earth, the formation of landforms follows a well-understood process. Rocks break down into grains. Wind carries these grains to specific areas where they accumulate, shaping the landscape over time. However, this process on Titan remains enigmatic. Titan's sand grains, unlike Earth's, are weaker and seemingly more ephemeral. Despite their presumed temporary nature, long-lasting sand dunes have been observed on the Moon. Wind-transported sand grains are expected to collide with each other and the surface, typically leading to their gradual diminishment. So, how do these grains persist long enough to form substantial landforms on Titan? The answer lies in a unique sedimentary process known as sintering. Through sintering, neighboring grains collide and fuse into larger, more durable pieces, making them resilient against wind erosion and allowing them to accumulate into the significant dunes observed on Titan. Given the adaptability of sand on Titan to form intricate landforms, one might wonder if life could have similarly adapted to this alien environment. Despite the many parallels between Earth and Titan, the primary challenge lies in Titan's unconventional ingredients. On Titan, what serves as water on Earth is replaced by liquid methane and ethane, encompassing its clouds, rivers, lakes, and seas. Nonetheless, Titan remains a geologically active world. The dynamics of flowing liquids on Titan's surface involve sophisticated physical processes. Analogous to Earth's water bodies, Titan's methane lakes can stratify, forming layers based on density variations. Furthermore, these liquid methane and ethane lakes could potentially experience eruptions. Such eruptions occur due to the interaction between methane, ethane, and nitrogen, creating bubbles forceful enough to sculpt river deltas within Titan's liquid expanses. Studying bubble formation in Titan's lakes aids scientists in deciphering the behavior of liquids on this captivating moon. Imagine a future scenario where a submarine is deployed to explore Titan's lakes. The heat emitted from the submarine could trigger an explosive outburst of bubbles similar to those currently being investigated by scientists. These discoveries not only enhance our understanding of Titan, but also indicate potential challenges that a spacecraft might face while navigating these extraterrestrial waters. If life forms exist on Titan, they would indeed possess a completely different biology, unique from anything we know. Researchers at Cornell University have posited that it is possible for cell membranes to form under Titan's current conditions. On Earth, cell membranes are composed of phospholipids, special molecules with a head and a tail. The head exhibits polar magnetic characteristics, with a positively and negatively charged side, while the tail remains nonpolar neutral. In water, these molecules arrange themselves in a bilinear, much like a sandwich. The head's bread slices face outward, interacting with the water, and the tails fill in hide in the middle, avoiding water. This structure endows the membrane with flexibility, crucial for life. Given the absence of water and the prevalence of methane on Titan, a molecule with an even charge distribution, the conditions to form Earth-like phospholipid membranes are not present. Thus, any hypothesized Titanian life would require an alternative way to construct cell membranes. Intriguingly, scientists have managed to create inside-out membranes in non-polar liquids akin to methane in laboratory settings. These membranes, though not identical to Earth's, could theoretically serve a similar function on Titan. Titanian membranes would lack the phosphorus and oxygen typical of Earth's phospholipids due to the Moon's frigid environment and distinct chemical makeup. Instead, scientists speculate that a different type of molecule could provide the structural basis for these membranes. One candidate is acrylonitrile, a molecule that could potentially form stable and flexible membranes in Titan's methane-rich environment. Researchers have explored the properties of acrylonitrile, finding that it can form structures called azotosomes, which bear some functional resemblance to phospholipid bilinears. Such molecules show promise in enabling the potential for life on Titan in ways that adapt to its unique conditions. The atmosphere of Titan, despite being predominantly composed of methane and nitrogen, also includes trace amounts of various compounds. Computational models have indicated that acrylonitrile is one such compound capable of forming cell membranes in the non-polar liquid methane environment of Titan. The Cassini mission detected acrylonitrile at levels of about 10 parts per million in Titan's atmosphere. Remarkably, these Titanian membranes, despite forming at vastly lower temperatures than their Earth analogs, exhibit qualities like stability and internal resistance to external forces, suggesting they could indeed persist in the frigid methane lakes on Titan. If methane-based life could exist, it would revolutionize our search for extraterrestrial life. Rather than exclusively targeting planets within the habitable zone of stars, those with Earth-like conditions, we would also consider more distant worlds where methane remains liquid. This would significantly expand the number of potential sites for finding alien life within our galaxy. Imagining a world where complex organisms evolved in such environments brings to mind creatures from fantasy movies and books, turning science fiction into a plausible reality. Even if surface life is unlikely on Titan today, there's a tantalizing possibility of life existing in the subsurface ocean of liquid water beneath Titan's thick icy crust. Scientists are investigating whether organic compounds from the surface could penetrate this icy shell and mix into the underlying ocean. If this exchange occurs, the subsurface water could potentially support life, However, much remains unknown about this hidden ocean, such as its density, composition, temperature, and interactions with the ice above. One crucial question is whether there is a source of chemical energy to sustain metabolism. Interestingly, there are bacteria on Earth that exhibit rare metabolisms, potentially capable of surviving in Titan's subsurface ocean. These extremophiles organisms thriving in extreme conditions offer a promising template for the kinds of life forms that might exist beneath Titan's icy crust. This tantalizing possibility drives ongoing scientific inquiry and future missions aimed at unraveling the secrets of this distant moon. It's captivating to think that billions of years ago, Earth's atmosphere was similar to what we observe on Titan today, with abundant nitrogen, CO2, and water vapor. These primordial ingredients could have played a crucial role in kickstarting life on our planet. Titan, in this sense, serves as a natural laboratory for astrobiologists to study how these components might have influenced the origin of life on Earth. There's a tantalizing thought that, given enough time, Titan could evolve into a habitable world, brimming with life forms reminiscent of those on Earth. The upcoming NASA Dragonfly mission, slated for launch in June 2027, promises to bring us closer to answering these compelling questions. This robotic helicopter will probe Titan for water or hydrocarbon biosignatures, providing vital clues about the moon's subsurface ocean and its overall potential for supporting life. Dragonfly's findings could significantly advance our understanding of whether the necessary ingredients for life are present on Titan and how they might interact to create a habitable environment. Imagining what alien life on Titan might look like is an exhilarating exercise. Given the unique conditions of Titan, any indigenous organisms would likely be vastly different from terrestrial life. They could have cell membranes of acrylonitrile, metabolic pathways suited to the cold methane environment, and features adapted to a low-temperature, high-pressure habitat. These alien creatures might resemble fantastical beings from our imagination, offering a fascinating glimpse into life's potential diversity throughout the cosmos. Stay tuned for more updates, and don't hesitate to share your thoughts on what Titanian life might look like in the comments below. The discoveries awaiting us in space are bound to be thrilling, and we can't wait to explore them with you. Thanks for watching.